secara mineral processing, kemudian menghasilkan selain yang memang core untuk pertambangan secara umum gitu ya. Nah, kita berusaha untuk mengarah kepada pembuatan nanostruktur yang mengarah ke sana ya, untuk photocatalysis, kemudian untuk tetap di solar cell, maupun juga kalau dia juga bisa berfungsi untuk di hydrogen generation itu. Nah, mungkin nanti kalau dari hasil inian bincang-bincang hari ini, talknya Mas Rachmat Adhi ini bisa memberikan insight lah buat kita semua, arahnya di sana tuh seperti apa. Nah, kemudian kita lebih nanti, oh ya, apa yang bisa kita lakukan di sini kali gitu ya. Jadi think globally and act locally lah.
Locally. Saya kemarin sempat diundang bicara juga di Tekmira, Pak, Bandung.
Oh, Bandung. Ya.
Tentang perovskite. Tapi ya begitu, mungkin harus ada miskonsepsi juga ternyata ya, kalau dipikir-pikir, kalau misalnya kita mengandalkan mineral lokal gitu ya, maksudnya mineral yang berasal dari kita sendiri, ternyata persepsinya adalah mineral alami. Jadi kalau mendengar kata perovskite itu kan ada barium titanite gitu kan, seperti itu kan, yang memang secara alami memang bisa ditemui. Tapi persepsi teman-teman di Tekmira waktu itu adalah perovskite solar cell itu dari yang alam gitu, dari langsung mineral dapat gitu dari alam, terus kemudian bisa dirubah jadi perovskite dan bisa dimanfaatkan jadi solar cell. Padahal kan mungkin material engineering, functional material itu kan sebenarnya semuanya sintesis ya.
Iya.
Semua sintesis titanium oxide itu ada di alam, tapi untuk keperluan device itu adalah bentuknya sintesis. Iya, jadi ya ada beberapa, mungkin itu yang agak sedikit perlu di public awareness-nya harus dibangun gitu. Kalau mineral itu bukan berarti mineral yang langsung diambil gitu.
As it is gitu ya.
As it is ya.
Ya, pembagian kerjanya sudah mengarah ke sana ya. Sebagai contoh di metalurgi dan material kan mereka juga memang memfokuskan bagaimana cara extraction-nya itu, mineral processing. Nah, begitu udah jadi sebagai contoh dari ilmenit kan ya, FeO2 itu. Nah, dari pasir timah Bangka kemudian diambil itu ada ilmenit, salah satu byproduct-nya, kemudian sudah diolah dan di fokusnya LIPI metalurgi dan material itu bagaimana bisa mengolah dari si ilmenit itu menjadi titanium oxosulfat gitu kan, TiOSO4 itu. Nah, udah sampai tahapan sana, kemudian TiOSO4-nya itu mau jadi TU dan nanopartikel. Nah, itu mungkin berapa persentase yang bisa diperoleh. Nah, sebenarnya itu sampai tahapan sana pembagian tugasnya sudah cukup bagus tuh, sudah selesai. Nah, kemudian bagaimana kita mengembangkan menjadi nanostruktur TO2, apakah tetap dengan nanopartikel kah, atau tetap menjadi nanotube atau nanorod dan sebagainya. Nanotube terutama mungkin bisa dari nanopartikel dirubah menjadi nanotube kan dengan hidrotermal biasa, itu kan juga. Nah, itu rangkaian itu sebenarnya harusnya seperti itu gitu. Nah, agak surprising juga kalau misalnya teman-teman Tekmira bisa menganggapnya bahwa take it as it is dari alam kemudian langsung bisa dipakai, ya kayaknya nggak gitu ya. Maksudnya tetap kita harus memikirkan itu harus dirubah dulu menjadi intermediate phase, menjadi precursor yang setelah itu mau katakanlah mau dengan cara hidrotermal, dengan cara sol gel, dengan cara surfactant templating, nah itu baru menjadi nanostructure material kan, kira-kira harusnya gitu.
Iya, ya itu yang kemarin saya juga agak kaget karena Tekmira kan memang teknologi mineral ya, mineral dan logam atau apa itu kan. Terus kemudian mereka melihat banyak source, banyak sumber buat perovskite dari struktur apa kayaknya barium titanate mereka yang melihatnya. Tapi ya itu apa namanya? Yang terjadi itu setelah saya ngasih tahu kalau itu perovskite-nya itu bukan alami, akhirnya mereka baru sadar gitu, crack kayak. Padahal kita presentasi 3 jam waktu itu.
Tadi udah berbuih-buih sampai ujung baru terasa, ya, ternyata beda gitu ya. Berarti sebenarnya berarti apa yang kita lakukan di sini dan kemudian juga kita sampaikan kepada para mahasiswa kita itu sudah on the right track ya Mas Adhi, untuk membangun tadi awareness tadi bahwa kita memang sebagai seorang materials engineer perlu merekayasa itu melalui proses sintesisnya itu gitu kan. Dari situlah kemudian masuk apakah dia mau dipakai sebagai bulk material ataukah sebagai nanostructure material kan gitu kan. Itu ada tahapan memang perlu sequence lah gitu. Kira-kira seperti itu ya. Mudah-mudahan itu yang message itu yang bisa terus kita tanamkan dan juga memang bekali kepada para mahasiswa kita, karena memang nanti skill, design skill dalam material itulah yang memang menjadi ciri khas lulusan dari Departemen Teknik Metalurgi dan Material itu.
Iya, seperti itulah. Memang ya di mana-mana material itu kan pekerjaannya sintesa, tapi sekarang gravitasinya itu kan semua kan supplier ya. Kalau kita kalau di Eropa itu kita akhirnya mungkin karena faktor labor cost juga seperti itu kan. Terus kemudian faktor supply cadangan mineral itu nggak ada di Eropa gitu kan, adanya di benua lain. Semuanya ada tapi nggak di Eropa. Nah akhirnya kalau dari Eropa itu akhirnya mainnya di level yang lebih ke arah device sebenarnya. Jadi dibanding dengan kalau Cina kan masih mainannya mineral processing, dan mereka sekarang karena ada cadangannya sendiri gitu kan, jadi lebih. Jadi akhirnya kita kalau di Eropa sih, kalau menurut saya kita nggak terlalu main di sintesa dari ore sampai yang ininya ya, sampai elemen ya, tapi lebih memanfaatkan elemennya gitu loh. Jadi sebenarnya sih ya kesempatan semua bidang sih ada, asalkan kita jeli aja sih. Iya, ya seperti itu.
Oke, mungkin bisa dimulai aja ya, Prof ya.
Silahkan
ambil
Pak Zaki.
ini.
Iya, Pak Zaki.
Kebetulan barusan saya kontak ada yang masih lagi jalan juga.
Iya, ya nggak apa-apa, kita mulai saja. Kan sudah Pak narasumbernya sudah ada di sini, sudah dari tadi siap beliau. Silakan Pak Zaki untuk dibuka dulu.
Sambil minum kopi nggak apa-apa ya?
Iya.
Silakan.
Ya. Baik, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang. Selamat pagi untuk di Austria, Pak Dr. Rachmat Adhi Wibowo. Mungkin saya buka dengan bahasa Indonesia saja ya, Pak, biar lebih mudah. Ya, jadi hari ini dalam acara rangkaian visiting Diaspora. Jadi hibah dari Universitas Indonesia ada rangkaian mengundang Diaspora yang bekerja di institut atau fasilitas riset di luar negeri untuk memberikan kuliah tamu untuk hari ini. Desain awalnya memang untuk kelas material elektronik, tapi tetap dibuka secara umum. Jadi dari peserta dari mata kuliah di luar MK material elektronik dapat mengikuti kelas tamu ini. Jadi untuk pembicara kita hari ini ada Dr. Rachmat Adhi Wibowo. Jadi Dr. Rachmat Adhi Wibowo ini sudah mempunyai pengalaman 10 tahun di bidang riset untuk lapisan tipis dan smart coating, terutama untuk fotovoltaik. Jadi selama PhD Dr. Rachmat ini menginvestigasi material fotovoltaik berbasis selenium, dengan proses solid state, reaksi solid state untuk mendapatkan lapisan film casterite dengan proses selenisasi dari proses sterilisasi untuk prekursornya. Jadi pengalaman Dr. Rachmat ini sudah pengalaman sudah mulai mungkin sekitar 2009, jadi lebih dari 10 tahun. Jadi selama 10 tahun ini Dr. Rachmat sudah berhasil mempublikasikan lebih dari 20 artikel peer review pada jurnal terkemuka, dengan lebih dari 30 kontribusi internasional pada bidang solar cell, kemudian pada beberapa international conference, salah satunya PVSEC, IRSI European MRS Meeting, kemudian IEE Conferences. Jadi Dr. Rachmat ini juga ditunjuk sebagai reviewer pada beberapa jurnal, salah satunya jurnal Semiconductor Science and Technology, Thin Solid Film and Solar Energy Material, dan Solar Cell. Jadi hari ini Dr. Rachmat Adhi Wibowo akan membawakan materi materials design for artificial photosynthesis. Intinya converting sunlight into non-fossil fuel for combating climate change. Dr. Rachmat Adhi Wibowo, waktu dan tempat kami persilahkan. Halo.
Ya, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Alhamdulillah. Thank you very much, Professor Herman, for your invitations, and thanks, Mr. Zakiuddin, for your for introducing me to, I think, to the brilliant students here in the atmosphere of let's say new era or a new normal. Everyone say that. Yes, thank you for having me here. And like Mr. Zakiuddin said previously, I would like to, let's say, give a talk, or maybe just an introduction to have a nice discussions here about the artificial photosynthesis, as you said in the poster, in the flyer for these international classes, yeah, in the program for metallurgy and material science departments. Yeah, since I was asked to give the presentation in English, so I think I will try my best because living in Austria, where English is not also a main language here, then your head has a lot of words. Yeah, so in the morning I wake up, I speak Indonesian with my family. I came to the office every day. I come to the office every day with sometimes mix between German and English. And suddenly I was asked to deliver a talk in English. So I believe that it will be a bit messy because every word mix up between German and English. So, but yeah, of course, I think it would be very nice to let's say, to contribute, let's say, to the educational quality of the materials and metallurgy and material science department in the University of Indonesia with this activity. And let's see what next. Yeah, I would like to, yeah, at the end perhaps discuss with all of you about the materials, about the processing related to the title. Of course, today it's artificial photosynthesis, or perhaps a bit about climate change, a bit about the what should we do and everything in the span. Maybe we will finish it in 2 hours. I don't know. It depends on the discussions. But I prepare this for, let's say, 45-50 minutes talk. And yeah, it's nice to see all of you this morning. I just finished my breakfast here, and I'm today working from home. So I would like to let's see if I can perhaps here share my screen. I hope everything would be fine. Yeah. All right. So this is I chose this perhaps how can we all right, this one, just maybe laser pointer will be helpful. Okay, it will be helpful for us today. So this is the title is about actually just to come to the issue of global issue, let's say, about the climate change. But I believe that climate change issue, global warming, is not really an issue in Indonesia, because the issue is different for sure. The priority of tackling the societal issue is different, and the problem is also different. But please believe me that in the future, maybe in 10 or 15 years, or perhaps a bit longer, like 20 years, like in 2020, 2050, I mean. So I believe that the climate change will be an issue everywhere. So European Union started to tackle this issue just about 10 years ago, actually, but now it's getting more intensive because of a lot of reasons. It's not only about the some kind of the the global warming is a fact, that you can measure it as let's say as the melting of the ice caps in the North Pole reduce 50% of the number of the mass of the ice there, and then as the data shows that the temperature of our planet increases a lot in the past, let's say 100 years, and the difference of 0.8 is a lot actually, because science prove that a lot of marine life, not only ice caps, are destroyed so far. And we have a lot of issue regarding the weather issue, about the water, fresh water supply everywhere, including to Indonesia, and that relates to the climate change as well. The change of the path of the storm in the, let's say in the Filipina, in the north or south of Filipina, or in the Mexico and Cuba area. So this is one of the effect of the climate change actually, which unfortunately becomes let's say a daily basis issue talk in Europe, in European Union, in Austria also, because everyone seems that they are aware of this issue, that it is really matter in the future. So there is a race right now happening in European Union that they try to reduce the carbon emissions, and they target, they set a target about how to reduce the carbon emissions in 2050, which is about 50% or 20% lower than the number of carbon emission in 1990. So it's not 20% reduction from 2000, but it's from 1990, which is, I think it was the time where Rio de Janeiro climate conference held. It was in 1992 actually. So this is one of the driving force why European Union try to set the, let's say, the scientific technological leadership in having everything, including the industry, including the economy, including the material science. So this is the basic kind of the driving force that try to tackle a worst case scenario for the carbon emissions in globally actually. So there are at least 3 scenarios, and we are trying to reduce the carbon emissions, let's say, compare with the 1980 actually level. And then you see that the causes of all of this basically is anthropogenic, which is causes by human activity. And you see that the contribution of the fossil fuel, of course, still the major causes, the main factor drives the increasing of the temperature of our planet. So there are coal, for sure, there's a fossil fuel, the oil, gas, some others like biomass and so on. But sometimes deforestation, in case of Brazil and Indonesia, this is the leading causes of the carbon emissions. So it's not about the fossil fuel, like in case of Indonesia, like from the cars, automobile, and so on, but it's from the deforestation. So we make a plantation for the palm oil and so on, and that makes at least contribute to the carbon emission globally. But the scenario how to do this is a lot of debate. The basic things is like let's say just to plant more trees and reduce cars, or use the electric vehicles, or not doing anything, just use bicycle to go for work and so on. So this is one of the every alternative are, of course, is possible for mitigating or for combating climate change, that at least to contribute to the reduction of the carbon emissions. But the question is there any systematic way, scientific way, technological way that also contribute to economic activity? especially to research and development, because the economy will be dead without research and development. And it must be a very drastic measures, drastic a program that is able to reduce significantly the carbon emissions. Like you see that if we just try to make a carbon emission level is the same every year, then the number of the carbon emissions globally is still there, still in the atmosphere, and we are not able to decrease the planet temperature. And the ice melting and weather change, everything is still occurs there. Yeah, so that's why we need to do some drastic measures. So here is the idea. Actually, of course, if you want to reduce the carbon emissions, carbon dioxide, just plants a plant. Yeah, I mean just grow plants, and then they just doing naturally what we call the photosynthesis, because the carbon dioxide will be changed or will be converted into glucose and oxygens. So this nature works. This is how nature works. And of course, without the solar energy, without sunlight, so you cannot alter this reaction to form the glucose or oxygens. So this is, of course, the easiest way to reduce the carbon emission is just to plant a lot of plants, so million trees and so on, and then we expect the carbon emission reduces significantly and help to maintain the planet temperature, or even to reduce it. Nevertheless, it's of course it's difficult, because the land used now, let's say, full with houses, with the industrial complex and so on. Some also change into some oil palm plantation, let's say, in case of Indonesia, or in Brazil, it becomes the natural rubber plantation. But now it's we need something to tackle the problem of climate change, the problem of carbon emissions in faster way. So because you grow the plants, it takes tens of years, let's say 20 years, until it works effectively. So the idea is just to use the concept of photosynthesis, try to use the solar energy, the sunlight, and combine it with oxygen and carbon dioxide, and then convert it into something useful. In this case of the glucose is something useful. Glucose, it's energy actually, because it contains a lot of minerals and a lot of elements that if we take it as a food, let's say, then it breaks into the energy, into the calorie that we need for daily activity. And the things from the sugar is not only it is eatable, you can eat it, but also it's because sugar is transportable. So glucose and every single pieces of the product from the photosynthesis is transferable, is also transportable. You can bring it, you can take it, you can move it to every places. So one of the idea from this natural photosynthesis is actually you can keep you can store, basically you can store the product of the photosynthesis and then keep it as long as you want. Yeah, like we keep rice, of course, and then it can perhaps 1 month in our house before we use it. So this is a kind of the transfer of energy from the oxygens, from the carbon dioxide in the atmosphere, helped by the sunlight, and then something occurs from it, and we use it. So this is one of the every solar energy scientists or photovoltaic or solar cell scientists are like really like this map and like this fact. Yeah, this is the fact that actually the solar irradiation, the sunlight that shines us every hour, every day, actually is much huge, much bigger than our consumption of energy in a year. So this is the calculation in joule. the amounts of energy per hour from the sunlight is much bigger than the consumption of entire human in a year. So this is Department of Energy calculate this, I think 2 years ago. And until now it's fine. Until 2020, the number would not change so much. So actually this is some kind of provocation for every, let's say for material scientist, actually, from materials engineer, that if we can able to use just 1% of this number per hour, then actually you can use the entire sunlight energy for lighting our civilizations in an entire year. And how much land, how big land do we need for converting this sunlight? Because converting the sunlight related to the area. So actually it's like in the Sahara, you just put some dots. In the case of size of, let's say, Borneo Island, and then you got electricity supply for entire years for all humanity. This is one of the crazy idea, basically, but at least it shows us how solar energy, the potential of solar energy for our source of energy, for our source of electrification, of our source of civilization, at least. So this is actually what we so far use from the solar energy is only about a fraction, a tiny fraction of it. So let's say if 430 times 10 to 18 joule per hour is equals, I'm sorry, the 110 times 10 to 18 joule per year is about 36 terawatts electricity that generated, that's consumed by the human in a year. So maybe we just, it is equal to only 1% of the energy delivered by the sunlight. So this is just in case if you want to use only 1% of the energy, then it means that you fulfill the entire civilization with unlimited and renewable energy. And this is also perhaps for your considerations, let's say, how the solar irradiation actually shines Indonesia and my place right now. And of course, comparing these two, it's not apple-to-apple comparison, because the geographic location of Indonesia in the tropical line, and then the geographic area of Austria located in the north of the equator line. So here is, for instance, here is Wien, so it's Vienna in English. So this is my place now. So actually the highest solar irradiation of the power that deliver from the sunlight, maximum about 1.4 megawatts per meter square per year. So it's 1.4 megawatt per kilowatt per meter per square in a year. The highest solar irradiation in Austria actually related to the lowest solar irradiation in Indonesia. So it's a 1.4 megawatts per meter square per year is the lowest part, and it is in the mountainous area in the West Papua. But if you see the average, perhaps the orange line is about 2 or 1.8 megawatts per meter square per year. So this is I think it's enough to convince us that the solar energy should be utilized more intensively in case of Indonesia, because in Austria, the size of Austria is just maybe the size of South Sumatra plus Jambi or plus Riau, I think. But the installed capacity of the solar cells, let's say if I talk about solar cells, is about 750 megawatts right now, as the time we speak. But in Indonesia, as far as I recognize, so there is only 680 megawatts installed solar cells capacity, which is really really difference. It's huge difference because the population itself is about 30 times larger, but the solar cell installed capacity is lower than in Austria. So this is opportunity actually in case of business, in case of engineering, technology, and research and development. So that's just one to motivate you to study about the solar energy and conversion of solar energy into something useful. So here is the scenario actually. So let's say the problem is how to storage energy from the renewable energy and using photosynthesis like the plants, like the trees, and utilizing sunlight in order to mitigate or combating climate change. So the scenario here is actually, so every scenario of the electrical grid or electrical distributions from the power plants, you see that it includes the same word everywhere. So it is it's actually the storage. As I said before, that the sugar or the glucose is something that can be stored in form of energy, in form of food, let's say. And then if you see the scenario of the electrical grid, electrical distribution, so it always used the electrical storage. Of course, we know this. Why? Because once you produce the electricity or energy and it is in excessive amounts, you cannot just throw it away, of course, because it will be waste time, waste money also. It's wasting everything. So now we think about something that can storage all of the energy. Of course, if you think about storage, then you always think about the battery for sure. But the battery is it's different thing. So it cannot be transferable easily if you want to use the electricity for a power plant. So it's always just stationary, something like that. But if you have electric vehicle like the Tesla or something else, then you basically you bring your battery everywhere. So this is the reason why electric vehicle is really popular now, not only in the technology in the in the industry, but also in terms of the scenario of how you storage energy, how to transport it. So this is all of the scenario that has the same point, which is in terms of the energy or electricity storage. So how you storage the energy. The problem is if you are material science, then you always think about how to storage the energy, making a new type of battery, or maybe if you hear about the carbon nanotube, graphene, and all of the exotic materials that can store the energy, then you are in the line. You are in the direction of the future. There is another case, but now we try how to storage or to generate something, the energy that can be transferable, and even you can use it by yourself by the time you produce it. So this is the scenario actually, how if, let's say, if we can mimic or just to copy paste what happens inside the leaf, in the trees. So they convert the leaves convert the carbon dioxide and water into storage energy, store energy that can be stored, and then with the help of sunlight, which means that you store the energy, you use something processed without carbon emissions, because photosynthesis and artificial photosynthesis does not produce the carbon emissions for sure. And then it should be from the renewable energy sources or sunlight. So this is the idea of how artificial photosynthesis looks like. So then the question is how to do it. So I'm not biologist. I'm not from the biologist or from microbiologist, like background, let's say. And then actually there are two what I can say at the moment. So first is biological approach. They use the enzyme or bacteria, and then they use the sunlight to convert the carbon dioxide and water into the chemical substances. So it can be methanol, it can be alcohol groups, it can be something else like acid, like the chemical substances that it's useful for industrial chemicals. But since we are materials scientists, materials engineer, so I would like to talk about the materials approach. So actually the materials approach is try to convert the carbon dioxide, water with the help of sunlight into three forms. First is electricity, and second is hydrogen and oxygen, of course, and then some useful chemical substances. So for this, I tried to prepare my presentation, my talk in a workshop style. So a bit kind of detailed step-by-step approach, explanations. But I believe that even Professor Herman knows these concepts, and maybe you got it already in the lecture there, and it's just a refreshment, let's say. So there are at least 4 technology for converting the solar light, let's say sunlight, into something else. Of course, you know the photovoltaics of solar cells. This is actually my background. So I made the solar cells from the materials, and then try to measure the performance, what is the efficiency, what is the current density, and so on. And then with the same materials, actually, you can do what we call as water splitting. So it is something like artificial photosynthesis, because you use light in order to convert the water or H2O into something else like the hydrogen and oxygens. The water splitting use electric bias basically. But if you can have a really nice materials, very exotic materials that can be act as a leaf just by shining it with the sunlight at the right wavelength, and then it converts water into the same hydrogen and oxygen basically without any electrical bias. Unfortunately, this is really rare, and like for instance, if you hear about the titanium dioxide or titania, which is the most popular photocatalyst for water splitting, to change the water into H2 and O2, the band gap position, the electronic properties of the titanium dioxide only accommodates the UV light, because of the UV light has the energy more than the energy band gap of the titanium dioxides. But this is also promising, and is really active research topics in this time. And the other is solar fuel. What we call is solar fuel. So solar fuel is just a term to convert the solar energy into chemical fuel. So everything about chemical fuel, like methanol, ethanol, in this case is formic acid. The formic acid is used by the chemical industry to produce something else, because the formic acid is something that intermediate product, chemical product from some elements into industrial chemicals. So this is really interesting, and we have currently a project for this. We have basically all of the project with all of this for technology. So this is the great idea, let's say, a bit ambitious, because so far it is a bit difficult at the practical point. But let's see, this is still on the very basic step of, let's say, fundamental research. So basically, this is the photocatalyst or photoelectrochemical cells. Basically, it's the same, except that the photoelectrochemical cell, if you see here, they apply a current or voltage or electrical bias. So basically, you just transfer the, you connect two semiconductor. One is the semiconductor and the other is perhaps metals. And just check whether which one is positive and negative, and then apply a bias about 1.5 to 1.7 volt. You can do it in the I think in the corrosion lab, yeah, in the corrosion lab in metallurgy departments. I was a laboratory teaching assistant for corrosion practice there, so I know the facility. I'm not sure that it's changed now or not. So you can apply the electrical voltage here, and then basically you can produce one in the cathode is oxygen, and one in the anode. I'm sorry, in the anode is oxygen, and one of the cathode of the hydrogen. Basically, the problem how to store it is not as beyond of this presentation, but basically this is just a bit of technical issue. So you can just cover this with the glass, and then the oxygen will be collected. So I think you know the basic fundamental working principle of photovoltaic, photocatalyst, or photochemical cells. The basically is just when the energy of sunlight comes to your materials, to the semiconductor, it excites the electrons from the valence band to conduction bands, yeah, provided that the sunlight energy is much bigger than the energy gap of your semiconductor. Then depends on the positions of your conduction and valence band, which will be discussed after this. So you can either reduce the water or reduce the substances in the chemicals, electrolyte, or you can also oxide the water or electrolyte. So you generate the oxygen on this case, and then basically you reduce the water or electrolyte into the hydrogens. So this is the actually something that you are familiar with. And now it's from the basic point of view, the basic science point of view, we saw actually a much bigger picture, or let's say a vision for the future related to the storage, related to the energy carrier, the hydrogen, with the artificial photosynthesis. And at the end, actually, this is need to be reminded many times that we tackle the carbon emission problem and climate change. So basically here is why hydrogens, it's important right now, is from the basic science point of view. Once you're able to generate hydrogen and oxygen from water, so you generate a new type of energy carrier, which is safe, let's say, which is environmental friendly compared with the fossil fuel. And then you can transfer it for sure. And then you can even produce it with 3 different ways. So this is the electrolysis. It's the same like the previous picture, how you generate the hydrogens. So there are actually 3 types of hydrogen, if I may to introduce a bit. So if you talk about hydrogen, what we are talking about now is about how to produce hydrogen through a green process, what we call the green hydrogens. But there is another type of blue hydrogen, and the other type is green hydrogens. This is infographic is very nice. It's from the European Institute of Technology, actually European Innovative in Technology. Sorry, it's the initiative from European Union Commissions to promote the hydrogen research, basically. So actually, the green hydrogen is just you produce hydrogen from fossil fuels. So you can produce the green type of renewable energy from a dirty process, basically, which does not help the carbon emission reductions, because they just use fossil, like natural gas, and you do some what we call this reforming process in order to get away the hydrogen from the hydrocarbon hydrocarbon compound in the natural gas, and then you left the carbon away and then going to the atmosphere. So it does not help a lot for reducing the carbon emissions. The other way is to use the same route with the grey hydrogens, but you capture the carbons as a residual or the side reaction from the hydrogen productions. So instead of just leaving carbon outside to the atmosphere, you capture it, you keep it, and store it somewhere underground. So this is what we call the blue hydrogen, just to use the hydrogen with the old technology. And then you can use electrolysis process to completely produce the hydrogen using the green source of energy. Okay, so this is the things that we learning so far. And if you want to know at the current status of hydrogen production, so actually, let's say 96% of hydrogen so far, if you buy hydrogen bottle tank from the market, then you get either it is from the natural gas, or it's from oil, or it's from coal gasifications. Only small fractions, about 4%, coming from renewable energy itself. So this is opportunity. This is a big, huge driving force for having a research and development in solar energy related, let's say, research and development, or hydrogen productions, or even material science, because we just try to reduce the portion of something that increase the temperature of our planet. All right, so now it's. I hope I can deliver this in exact time. So now it's almost 15 minutes, I guess. So here is how do we choose the materials for artificial photosynthesis. So I think this is just a refreshment, let's say, fresh up for you who are already learning about the quantum mechanics, quantum physics, or quantum chemistry. So basically, what we need only three elements, of course. So you need the semiconductor, you need the metals, and you need the electrolyte. The electrolyte is, of course, water, containing, let's say, some kind of the chemicals that increase the conductivity of the electrolyte, like sodium sulfate or potassium sulfate, which is really cheap, affordable chemicals. So, and then, of course, this is just a refreshment for you, and the semiconductor can be P or N. It consists of valence band and conduction band. In between, you have what we call the band gap or energy gap, which is Eg. So the difference between conduction band and valence band, nothing inside in this area. So this is the things that you have to consider first if you want to design a materials for solar energy, because the solar energy mostly consists of a visible light between, let's say, 2 or 3 electron volt into 1 electron volt, roughly. So you need to have the materials that the band gap in between 1 and 3 electron volt, because electron can be excited only when the solar light, sunlight energy exceeds the energy gap. So we have for the P-type semiconductor, so Fermi energy is here, and the conduction band for, the N-type semiconductor has the Fermi energy here. So this is actually 2 materials basically. So I just put it in one diagram. All right, so and then we have another terms for designing or understanding electrical properties of materials. So the key here, or someone call this chi. So this is the distance between vacuum level to the conduction band minimum. So we call this as electron affinity. And we have the distance between the Fermi energy, these two Fermi energy, one is for N-type and one is for the P-type, we call this as working function or work functions. So work function of the P-type has deeper or larger than work function for N-type semiconductor. And this is another terms that which is a bit not really relevant for us now, but this is the distance between the vacuum level to the valence band. We call this as ionization energy. So if you forgot what is the definition of electronic affinity, electron affinity of materials, work functions, energy gap, and ionization energy, it's better to use the diagram like this. In metal, everything is the same basically. So all the Fermi energy of metals, the work function of metal has lies at the same energy level. So, but we always talk, in case of metal, we always talk only about the work functions. So the work function first was discovered by the Einstein for his photoelectric effects that brought him a Nobel Prize at the time. So this is for the electrolyte. So the electrolyte you can measure the redox couple. Yeah? So it should be an equilibrium sign here, but I couldn't make it. So it's actually it's two-way reaction, the equilibrium. So you can also measure the redox couple from the vacuum level. But in terms of electrochemistry, you have another scale basically. So this is the scale of, if you use the reversible hydrogen electrodes, like in the chemistry or the electrochemical study laboratory, let's say in corrosion, you use the reversible hydrogen electrodes a lot. So this is the scale of positive and negative, and this is the reversible hydrogen electrodes. But for us, I mean, at least for me, if I study about solar cell, about solid state physics, so we use the energy level coming from the vacuum level. So we have two scales here. So one scale used by chemists, by electrochemists, corrosion engineer, let's say, and the physical scale used by solid state physics, semiconductor guy, and then materials engineering use the energy scale or physical scale, which is should be in the energy electron volt. So how to convert this? It's at the beginning a bit messy, a bit difficult how to understand, but at least we know it. So the reversible hydrogen electrodes, or you can also use the silver chloride reference electrodes. It's actually has a relation of about here, corresponding to the physical scale. So it's about 4.44 electron volt if you measure from the vacuum level here, but it corresponds to the 0 volt corresponding to the standard hydrogen electrode. So this is one of the conversions scale between these two. Why zero is for the hydrogen is because the electrochemical study comes much earlier than the quantum mechanics. So Einstein produced these in 1905, I guess, but the electrochemical study start in as early as 1800. So they didn't know what is the reference level. So just they put the hydrogen evolution, the hydrogen electrode, and put it as 0. And everything above and under should be measured again as 0. So that's only the historical point of view. All right, so why is band gap or band energetics of materials is important? Because you want to design materials for a solar fuel, solar cell, photocatalyst applications. You can select the suitable materials having suitable band gap for absorbing sunlight. You can predict what kind, this is much more important, what kind of reactions, whether it can release the hydrogen or oxygen, and which kind of materials, which materials that's suitable for electrolyte, and also anticipating which materials can behave as the cathode on anode in the photo device system. Of course, this is difficult to read, but first is, if I may, reading like that is 1.12 electron volt can absorb sunlight, because this is 1 electron volt. 1.5 is also, but now how is it do they work as the solar cell or photocatalyst or artificial photosynthesis? So this is another issue. So here is just the step by step, but I will not going into detail. I will we can discuss this in the Q&A session perhaps. So basically, if you have two semiconductor PN junctions, you want to make a PN junction, and this is the heart of the solar cells basically. So if you this is isolated p-type and n-type. If you connect them together or fuse together using fuse temperature, or you deposit one materials of p-type on n-type semiconductor, then the band adjusted, so it's aligned. So actually we have Fermi energy for p-type and n-type, but once they are fused together, so basically what you need is just to align the energy, Fermi energy of both at the same level, and the other is follows. So it's everything is just follows, and the Fermi level of their respective materials also follows. And what happened next is they make a smooth transition between all of the edges of the conduction and the valence band into what we call as a band bending. I believe that you learned this already, and everything is the same basically. So the n-type materials, n-type semiconductors still has the corresponding band gap, and the p-type semiconductors still have the same band gap as the original one, except the band bending. Then this is another metal n-type semiconductor. At the end, we will sum up these and how to understand how photocatalyst works. Yeah? So this is another type of junction between semiconductor and metal, and this is for the n-type. Of course, it's the same concept. At the beginning, the Fermi energy is equalized, and then everything is the same, except the position of the band a bit different now. And then at the end, if you bring these two materials together, at the end there is a smoothing of the bending of the band gap, in this case for the n-type semiconductor, and it's a bit up. Because you have the work function of the metals is on top of the working functions of your the n-type materials. So this is what we see, the reason why it should be like that actually. Okay, so this is metal and n-type semiconductor. It's just refreshing your memory basically. So this is a p-type of semiconductor, and this is the metal. And if you join together of these two materials, also the same, you equalize the Fermi energy of the p-type semiconductor and the Fermi energy or the work function of the metals in the same level. Everything are followed, and then there is a band bending, because you see that the vacuum level for the p-type and the metal a bit different now. So you make a band bending, something like that, and the other are follows. So this what will happen actually. So I forgot to bring this down actually. So I hope this is not really essential. All right, now how about the materials and the electrolyte? So this is a bit tricky, because there are a lot of what I understand, a lot of approach and a lot of misconceptions what I read, and it makes me a bit confusing also. But at the end, if you have an n-type, let's say in this case is n-type, and this is also what happened in the final case. So you have to align, of course, all of everything here, and then you see the band gap will upward because of the difference between the work function of your metal and work function of your, I'm sorry, the yeah, it's a work function of the n-type. So this is what happened in equilibrium. Just after you break, you bring together all of the materials into the electrolytes. And then this is the p-type. So it has difference. So this is in equilibrium. So once you put everything together in the electrochemical cells or electrolysis cells, and then everything aligned, so it just follow the same behavior like the p-n junction, like the semiconductor and metals. Now the useful things from learning band diagram, band bending of two different or three different materials is you know where the electron goes, right? So provided that if you shine your materials into the p-n junction of the two different semiconductors, then of course originally the electrons is located here. And then once electrons excited into the conduction band, then the electron sees the band bending down, right? So it's downhill movement of electrons, while for the holes is uphill movement in the valence band. This is the rule, is like the electron is like a bowling ball. I always remember like that. It makes everything easy for me. So ball is always downhill. Yeah, it's going down, and hole is like a balloon. It's always going up. So it's this is what the rule that I always use, and it works so far. So this is if you have a band bending like this, then you can predict where the electron goes. Yeah. So here in this case, the electron goes to the surface of the n-type like that, and then the hole will go back to climbing the energy level, because it is the difference. It is the up it's different behavior with the opposite behavior with the electrons. In this case, the n-type and metal junctions, you have, of course, here is the band bending is down. So once electron excited by the sunlight, so it cannot go in this way because this is uphill level. So you have to go to the left because this is a bit downhill, and the opposite part, the hole will climb up because it tends to go up if it sees the higher energy level. In this case is the valence band, and the others follows. In this case of the p-type electrolyte, just for example, if you excite the electrons by sunlight from the valence band to the conduction band, so the electron sees the level of the conduction band downward actually, so it getting lower, so the electron will go to the surface between the semiconductor and electrolyte, while at the same time holes will climb the energy level of the in the valence band, and then it goes somewhere here basically. And this is if you connect these two materials of p-type and n-type with the electrical wire, let's say from outside in the electrolyte in electrochemical cells, so the hole will goes there, making a loop going to the metal part, and then the hole climbs the energy level like in the valence band, and then reacts somewhere with the electrolyte, which is the principle of the photoelectrochemical cells. I hope I can finish in 5 minutes. I'm sorry if I talk too much. So here's the photoelectrochemical cells. So where is the cursor? Okay, this one here. So this is what happened actually in the photoelectrochemical cell, or in in photocatalyst or photochemicals phenomena actually. The differences between photoelectrochemical cells and photocatalysts or photochemistry is about the absence of the electronics or electrical wire. So here is what happened is, if you have photoanode, you can see from the Fermi energy level here, which means this is the n-type. And if you see the Fermi energy here for these materials, so this should be a p-type. So the p-type works as a photocathode, and the n-type works as photoanode. So this is what happened actually once you give light, the lamp with high intensity into your system, then the valence, the electrons from this n-type materials goes or excited up. It sees climbing in terms of energy level, so the electron cannot move there, so it should be going there and then make a loop over there and combine into the p-type semiconductor or photocathodes. So what happened with the holes here? Since the holes sees the energy climbing here, so it climbs, it goes up like a balloon, and once the hole attached in the surface of the electrodes, the water will be attracted here, and then it oxidizes water. So this is the holes, it oxidizes water and it produces the oxygens. And here in other case, in the photocathodes, in the p-type semiconductor, so differently behaves actually. So the sunlight excites the electrons into the conduction band. It sees the conduction bands bending downward, so it goes here, and in the surface, it reacts with water and it reduces the water into the hydrogen bubble. So you should see actually hydrogen bubble and oxygen bubble here. The difference between the photoelectrochemical cells and photocatalysts, photochemical is whether the photochemical requires electrical wire or not. So in case of photoelectrochemical cells, we need the electric wire. We need to have electric bias. So here is the materials, a lot. So in this case, you can choose basically which one behave as a p-type, which one behaves as the n-type, and here is the water level. So if your conduction bands above the hydrogen evolution level, so it will act as the hydrogen producer, let's say, in the photoelectrochemical cell or in photocatalyst or in photochemicals. If your valence band below the oxygen level, water oxidation level, so you will produce oxygen gas. So here in case of oxide materials, which are mainly n-type semiconductor, except cuprous oxide, this is cuprous oxide, this is the materials, p-type materials actually. So oxide materials, oxide semiconductor behaves as the n-type, and then normally they will produce oxygen if you put it in the electrolyte under circumstances, yeah, under several particular circumstances. But the p-type semiconductor, they always produce the hydrogen if you put it into the electrolyte in the photoelectrochemical cell or photochemical cells. And there are a lot of versions actually, if I have to remind you. First is one is the valence band and conduction bands picture, and the other is only a band gap picture. So don't be confused. This is just the way how the people actually works. So here is very convenient because you just need to draw the band gap while you just miss the conduction band and valence band, which is a bit different with this display. And the other is as well. So this is conduction is here, valence bands here, and in between what you see, what you are seeing now is actually the band gap. So here is the in case of cuprous oxide, let's say, because I'm telling you here because we are working with cuprous oxide. So the cuprous oxide and water, so it's just simply following the previous. So once light coming to your semiconductor, to your cuprous oxide, the electron excited into the conduction band, it goes down because the difference, because the energy level of conduction band here is lower. And then the electron will reduce the water into the hydrogen, and you see the hydrogen bubble there. So at the same time, holes just try to make a complete circuit going into the metals. And this is bismuth vanadite, which is really famous also for producing oxygen. So bismuth vanadite is an n-type semiconductor, and what happened is actually here, once the electron is excited into the conduction band, it goes there because it cannot climb, while the hole climb into the surface of the bismuth vanadite and electrolyte and react with water to produce the oxygen. So it oxidizes water basically. So this is the one of the example also. Just I took it from some review paper, and this what you see now is a band gap of different materials, what we call this casterite, copper zinc tin sulfide, or it's really long, so we always make it short as CZTS. The CZTS have a band alignment, so this is actually the band gap of CZTS, band gap of zinc selenide, copper, cadmium sulfide, and cadmium selenides. So it aligns and it works as the photoelectrochemical cells. So basically, this is what I don't tell you so far is about how to measure, because this is, I believe it's too much for the talk today. But at least if you want to see the photoelectrochemical cell works to produce oxygen and hydrogen, you can either capture the oxygen or hydrogen, or you can see the profile of the currents. So what you see is a photocurrent. This is the current because of the excitement of electrons from the valence band to conduction band, and then it's because you are shining your materials or photoelectrochemical cells with the sunlight. So this is, I think we can discuss this in the Q&A, but there, just sum up everything now, it's how to design. The trick is, of course, you still need a materials database, and there are a lot of collection of picture that makes everything easy. Which one is aligned, which conduction band is above the hydrogen evolutions level, which one is below the oxygen oxidation level, like this one. And you just have to search into the literature basically. So you are safe, we are safe, and then we can do it for making the materials itself. So how I make it, so this is the activity in our just 5 slides, 3 slides more for showing what is our activity in AIT. So basically this is one of the project that we got basically for flexible photovoltaics, but we use right now the zinc oxide and doped zinc oxide for making n-type semiconductor for photoanode in photoelectrochemical cells. So I use it. I use a spray pyrolysis. So actually it's a really nice precursor, because this is really really common. Just using the acetic acid as a buffer, and then everything is acetate based in the water. So I spray it at 300 degrees, 380 degrees, and then normally this is what I got. This is actually work from our students at the time, and I reproduce it for other application like the photoelectrochemical cells. And then the other is also interested for you. Maybe you can try it in the laboratory there in the Department of Metallurgy and Materials. Here is cuprous oxide. It's very active research it's very active materials for the photoelectrochemical cells actually. So it's cuprous oxide. The color of cuprous oxide is red with really nice in appearance actually. So it's the right color. The band gap is about 2 electron volt. Sorry, it's the laser pointer. So here is the band gap of 2 electron volt. So it works also well for the solar cells. And I deposit this cuprous oxide only using the electrochemical depositions. So from the solution of cuprous sulfide, lactic acid as a buffer and complexing, because you need to stabilize the copper If you don't use lactic acid, the copper will precipitate directly. And we use very high pH using NaOH, sodium hydroxide, at pH 12, which is a bit alkaline. And then what we see is after deposition is this layer basically, which is really compact. I think the deposition time is about 30 minutes. It depends on the voltage, so I can reach about 2 micron thick of cuprous oxide. This is really interesting because it works as a photocathode because this is a P-type materials. And the last one is another materials of CCTS. I made it using the ink. So this is the idea is to make basically a printable photoelectrochemical cell or printable solar cell. So it's solar cell that can be printed on flexible substrate like aluminum foil or titanium foil and so on. This is the process, and for the solar cell it works nicely. It's 8.2%, and this is how it looks like. And now we are trying. One of our students is trying to use this as the photoelectrochemical cells application. So at least this is normally many people says the devil is in the details. Yeah, you talk about hydrogens, you talk about climate change. It's really nice. Artificial synthesis, the concept is really nice. But as a students, engineer, and scientists, we need to go into detail. So this is the not funny part actually for the doing research. Basically, yeah, research anywhere, because the global picture is really nice. We need to go to combat to attack, let's say, the problem of climate change. We are doing in Austria now. We are doing this Friday for the Future strike. Yeah, so we demonstrate in the street before the pandemic actually, and then everyone takes part of it. But the problem is when we try to find a solution, then we have to deal with the science. So basically, I hope there is some funny part in this talk and some not so funny part. And let's say we can go for the Q&A, and I hope everything is understandable. I deliver many good things, hopefully, and let's say go back to Mr. Zaki for the moderation. Thank you.
Okay, thank you very much for the very nice presentation, Dr. Rachmat. So I think we will proceed directly to the other participants. If you have any questions or comments or anything regarding this lecture, you can directly. Oh, there is already one question from Maurice. Okay, from Maurice here we have, thanks a lot, Dr. Rachmat, for the presentation. I have a question regarding the hydrogen as the product. Hydrogen itself can be said to be synthetic gas. So in your opinion, what is the best application of hydrogen in Indonesian settings? And another question regarding the development of hydrogen economy. Russia has been inclining towards advancing their artificial photosynthesis. Do you personally think their advancement will significantly affect the awareness of artificial photosynthesis?
All right, thanks. I also read it in the chat room, I guess. All right, so I just turned my camera back, and then I saw a lot of metallurgy department lecturer here. All right, so I'm getting nervous now. All right, so from the point of view of hydrogen product, how can what is the application for Indonesian setting? So basically it's everywhere. I mean, everywhere is the same. I mean, the hydrogen application in Europe, in Japan, in South Korea, in Singapore, and Indonesia should be directed into the same application. So the hydrogen is what I said in the beginning, is hydrogen is the energy carrier. So you can carry it everywhere. It's like battery. So you can carry, you can switch into your like not battery. So it's how do you call this? A charger bank. So the charger bank contains the energy, and then you can plug it into your cell phone. Sometimes you can plug it also with your laptop. Depends on the charge bank technology and specifications. So this is what happened also with hydrogen in the gas form. So the gas form of the hydrogen can be used mainly for generating electricity. So in the what we call as the fuel cell. So the fuel cell technology is not only for cars. Actually, there are 4 or 5 types of the fuel cells. So the hydrogen can feed up into the fuel cell tank and combine with hydrogen. So you make the electricity. So this is what happened in let's say a big capacity of fuel cells. Normally now we use the PEM, proton exchange membrane fuel cells. So it works also as a small mini electric power plant, basically. So you can use that. So the hydrogen can be stored and then delivered to someone somewhere else who has these fuel cells power plants, let's say. And now it's getting popular. The other is, of course, the car. The car can use the hydrogen in case of when you use the electric vehicle or I'm sorry, the fuel cell vehicles. Everything is okay now. It's just connection is fine. All right, okay. Because I hear some big noise. So basically, the thing is the hydrogen is just the energy carrier. You can do what you want with this carrier actually. And the other is the advancing. Of course, this would be happy news. Actually, it's really nice news for us because the way science work or research work is always depend on the commercializations as a driving. So like if you are working with the photocatalyst and it is very exotic materials, it's very exotic topic of science, but at the end, no one use it. So it's just a very interesting topic for academic, all right? But when someone or a country, in this case, if you hear something from someone from Russia able to produce it and then the artificial photosynthesis and then marketed it or commercialize, make this product commercials, and then this is a good news that drive force that the proof of concepts of your photocatalyst materials for generating hydrogen, oxygen, or having can be applied as artificial photosynthesis also works. Yeah, so this is the things that very nice news basically for the photoelectrochemical or artificial photosynthesis community. So this is just my feedback. So from Moritz, yeah. All right.
Okay, thank you very much for the answer, Dr. Rachmat. Okay, for the next question, perhaps for another participants, or maybe from Dr. Alfian Ferdiansyah, not Alfian Shah.
All right, yeah.
No.
Dear students, please ask any question to Dr. Rachmat because he's an expert in this field. So this is a very useful time for you to have anything, yeah? Not only regarding the materials perhaps, but maybe some, previous experience how Dr. Rachmat can transfer himself from a metallurgy, become a very so-called maybe combination of materials and physicists, yeah, actually. Yeah.
Actually, we do everything in the lab, including cleaning the lab.
Yes, please. Ayo pada tanya. Ini kesempatan yang sangat bagus untuk nanya ke Pak Dr. Rachmat Adhi Wibowo.
Di Pak Alfian mungkin mau tanya, tapi suaranya nggak ada tadi Pak Alfian. Suaranya masih kecil Pak Alfian. Oke, mungkin Oke, mungkin kita ke penanya selanjutnya ada from Gusaimas Matahachiro. So thank you Dr. Ahmad for this presentation. Recently I have been reading several research and projects regarding carbon capture devices collecting carbon dioxide gas either from pre-combustion and post-combustion. So after listening to this talk, I was wondering if there are any past projects about integrating artificial photosynthesis with carbon capture storage devices.
All right, thanks for the nice, very nice questions. How can I call his or her name? Guamas, yeah, Gusamas.
Ago.
Ago. Okay, all right. Yeah, actually, I just want to maybe my presentation was not really clear in the beginning. So actually, carbon capture storage works for non-renewable. So it's for non-renewable energy technology, like if you are using coals, the power plant of coals, the power plant, or any industrial, let's say, which generate the carbon dioxide. You can see on the pillars of the stove, let's say, and then the carbon dioxide as a smoke, it's appear on the top of the stove. Then it is carbon dioxide for sure. And the carbon capture storage (CCS) technology tried to capture all of these carbon dioxide and store it somewhere, normally in below, actually in underground. So carbon capture storage works in every industry for capturing any carbon dioxide emissions. Any smoke generated from the industry, from the company, goes to the CCS and then it's stored there. Or use it like for, I think carbon dioxide can be used for, of course, how do you call, for the fire extinguisher. There is one of let's say it is one of the example of application of the carbon dioxide, but the artificial photosynthesis actually does not produce carbon emissions. So there is no couple between the artificial photosynthesis and CCS technology or carbon capture storage, because photoelectrochemical cell or artificial photosynthesis does not require the CCS. Or maybe the question is like this: instead of storing the carbon dioxide, so the CCS as a supply, I think this is what the question means. Yeah. So the CCS actually, all right. So the CCS supply the carbon dioxide for the photoelectrochemical cells or artificial photosynthesis, then it works for sure, because you don't need to capture the carbon dioxide by yourself. Just bring the photoelectrochemical cell outside and then just expect the carbon dioxide. So it works, of course, yeah. So but now it's maybe interesting for you if you have entrepreneurship spirit, let's say. So now there is a carbon trade, what we call this carbon dioxide trade. So it's trading between the developed country who emit a lot of carbon dioxide from their industries, and in the future perhaps there will be a trading between the carbon dioxide gas, delivering to any country, because any country wants to use the carbon dioxide as input for your artificial photosynthesis technology. Then it will be another another terms, yeah, another challenge basically. So now, if we think that the hydrogen is transferable for energy carrier, but the carbon dioxide also will be has economic value, something that out of the industry as a waste at the beginning, but now it's getting economically benefitable. So this is what I understand from your. I hope my my answer is correct. Okay. Thanks.
Thank you very much. How about it, Ago Gusaimas? Is it?
Yes. Yeah. You said it earlier yourself that my question was about how carbon capture devices could supply the carbon dioxide.
All right.
For artificial photosynthesis. But what I was wondering is, were there any past projects that actually applied these? Or
if you ask a project in AIT in our lab, no. Hello, all right. Okay, so for the project in the past in our laboratory, so we don't have it, but in the case of the project nationwide in Austria, there is some project, but I don't put it here. Yeah, so actually it's an active project for the CCS because this is the best and near term project to eliminate the carbon emissions faster, basically. So if you wait artificial photosynthesis until it's in an industrial or commercial scale, then it will take maybe a couple of years or maybe 20 years in the future, basically. Yeah, that's perhaps this is my feedback.
Okay, thank you very much. How about another question from participants or any comments? I think it's a good opportunity to ask a lot of things to Dr. Rachmat, since he has been more than 10 years experience researching in this particular research area, especially for solar cell. Anything from participants?
Here I saw my humble senior, Dr. Munir, and he knows me very well. And how are you, Mr. Munir? Everything is fine. All right. So I mean, if you have any questions, you can do it in Bahasa Indonesia perhaps, but I will try to reply it in English.
Oke. Dipersilahkan untuk yang lain. Ada yang ingin menambahkan atau komen? Tidak?
Our student is Sai Cat, Dr. Adhi.
Malu-malu kucing.
Yang malu kucing ya.
It's fine. So we have a chat box. So if someone.
Okay.
All right. So this is while we are waiting for one or two more questions, just I mean, I don't know. It's the priorities of course it's difference between the Indonesian community, scientific community, and the European, let's say. In my case, this is my point of view as the scientist working in Europe. But of course, one of the problem in Europe is, of course, materials, right? So we are. I think I published one review paper that actually contains the materials that really in the critical status. Critical means that it is really highly valuable as economic in economic terms, and then the other is but the supplier is really rare actually. I mean it's monopolized by several countries only in the planet. Like China produces rare earth, and Indonesia produces tin. Bauxite comes from, I think, from African country. Lithium from from Zambia and Australia and so on. So from the point of view of developed country, so we can produce this technology like photosynthesis, artificial photosynthesis, solar cells, and so on. But at the end, the one who control the materials, actually, the supply, the everything about the resources is the one who play quite significantly as well. As long as you can control, you can dictate the developed country. So this is nothing secret here that the European, Japan, and so on, and South Korea, they are really demand a lot of like materials like indium, for instance, because the semiconductor industry or device using indium. So this is the reason why European, in our case, we try to replace indium with the other materials, which has not been successful for so far. Yeah, I mean, indium is still the best materials for display technology, for the LCD and for so on. So in this case, perhaps what we discussed in the beginning of the Zoom with Professor Herman is at the end, the strength of Indonesian, like for materials engineering, is related to the mineral, to the materials itself. Yeah. So I mean, perhaps I can make the solar cells, but the materials of copper, zinc, tin, and sulfide comes from Indonesia. So this is why not we cut. You need to cut this process instead of exporting some minerals to Europe and they exporting the solar cell to Indonesia, and then why not you cut to produce. Just to produce these elements highly purity as possible, and then use it as the solar cells. So this is a long way actually for in case of Indonesia, but in European case we don't care about the mineral processing anymore, because European is not mineral processing is no longer a strength of European research development, because we don't have a mineral there. So in this case, for students, I guess, or opportunity dealing with the mineral processing, material science, until even photoelectrochemical cells, or perhaps a hydrogen storage using exotic materials are still open. Of course, it's open. And this is the advantage that actually, let's say it's not advantage, it's potential advantage, because we don't see this at the moment, but I think in the future would be that kind of a scenario. Yeah. So I hope this is correct, Professor Herman. So if you have anything to discuss about this matter, it's a nice time for me as well. Yeah.
Okay, I think there is a question from Dr. Alfian.
Right. There is another question from Dr. Alfian. So Dr. Alfian asked, do we have similar situation in PV? I mean, in PV now, the community are focused in one material like perovskite. In solar fuel research, do we have similar situation? We just focus on optimization, or we are still in material selection to obtain the best photo anode?
Thanks, Dr. Alfian. It's my long colleague. Spricht Deutsch eigentlich. So, okay. Yeah. So actually for PV community is different for sure, because I think if you talk about what we call the technological readiness level, I'm sorry. So the technological readiness level for PV and perovskite now it's above 7. I mean, it's much easy to go into the commercial stage, because silicon is already there since 80s, and perovskite is really fast developed in the past maybe 5-10 years, and now they are industry for perovskite solar cells everywhere. But of course, you're right that photoelectrochemical cells or artificial photosynthesis, as at the moment we talk, as we speak now, it's still on on very low level of readiness level, technological readiness level. So it's between 1 and 2, what we call as the basic science or proof of concept. So basic science we know since 70 from the first photocatalyst of titanium dioxides, but the proof of concept, it is a level of 2 or 3. So the proof of concept is just at the moment is to prove the materials works as a photoelectrochemical cell or artificial photosynthesis. So this is at the moment, and there is no industry work on commercialization of artificial photosynthesis. There is industry for producing hydrogen, like with the proton exchange membrane fuel cells that convert hydrogen and oxygen into electricity and water, the vice versa. But it is a different technology, and this is not artificial photosynthesis. The hydrogen comes from what I presented previously from the gray hydrogen coming from the oil industry. So at the moment, this is the reason, actually, the secret, Dr. Alfian, why AIT in our lab a bit shift from the photovoltaic research topic into the water splitting or photoelectrochemical cell or artificial photosynthesis, because the level of the technology now is not mature, and the materials for solar cell and the water splitting is the same. So you see that in my presentation, cuprous oxide, we use cuprous oxide for solar cells, but now we try to use it as artificial photosynthesis. And this is the material that I saw Dr. Munir studied so far, which is copper indium sulfide, copper indium selenide. So this is the materials that I know Dr. Munir is active for this, but it can also be used as a water splitting to produce the hydrogens. And since at the end, the industry also dictate the direction of research, like you are easy to commercialize your research product because there is a market for that. But copper indium sulfide, now the industry is really weak, actually, because the price of solar cells is decreased. So why do you use these materials for solar cells? Because you cannot compete with one. So at the end, it's I don't know if the University of Indonesia, if the metallurgy and materials department in University of Indonesia wants to catch or run together with the community, global community. So I think the artificial photosynthesis would be nice for sure. Of course, this is a basic science. Yeah, this is a basic science. So it means that the level is everyone is almost the same right now. So this is what I can give my feedback to you, Dr. Alfian. Thanks for discussion. It's really nice.
Thank you very much, Dr. Rachmat, for the nice feedback. Is there any other question from participants? This is very crucial moments because it is difficult to ask Dr. Rachmat to give lecture like this because it's a bit tight, the schedule from Dr. Rachmat. Okay, so we still have 14 minutes left. So I hope the participant use this opportunity at least to comments or ask anything regarding it. It doesn't have to be regarding this lecture, but anything related to the lecture could be addressed here. No?
Maybe one more information, just information from me,
Okay.
Dr. Zakiuddin. No, I mean, I hosted actually one student here for master course. Actually, it's not master course. It is a kind of guest lecturer, someone who tried to finishing his or her master thesis or bachelor thesis and do some kind of final project with us in AIT. So I hosted one ITB, Institute of Technology Bandung students a couple of years ago, 2 years ago actually, for doing 3 months research in AIT, for doing, at the time it was for solar cells. And he came and then he did a lot of things actually. At the end, actually nothing works because the technology that he chose for his master thesis a bit complicated actually. So at the end, of course, it's academic does not need to be really successful in terms of product and so on, but because the emphasis is different. But at least so far it works. So someone visiting my lab in Austrian Institute of Technology, doing 2 months or 3 months gathering the data, you can have access for almost every single analysis methods, like electron microscope, you can operate by yourself, XRD and photovoltaic performance test, any chemicals you need, and so on. We provided that. And it turns a really nice opportunity actually, because I have someone work for 2 months with the very nice topic, as long as the topic is aligned, it's in line with us. And then second is, I believe that it would be a very nice opportunity. The problem is the funding actually. So since AIT does not provide funding, so it means that the students came to us with his own funding, means that someone should back up or support the funding. It was the program for the campus from ITB, and it seems that's very nice if some of you perhaps eager to promote or to initiate this kind of program, and just 2 months or 3 months with us here, fully supported, except for the living costs for sure. So I mean, it will be very nice because it works, and at the end, the students will be my students for having a PhD degree. Next start will be inshallah, perhaps next March 2021, because he has this very nice curriculum vitae. He worked already in AIT for 2 or 3 months and do some joint publication and so on. So I hope this information can be useful for any of you. So, and the follow-up would be nice. Yeah.
Okay. So thank you very much. It's a nice opportunity. So we will consider to introduce this opportunity to our students here in metallurgy and materials engineering, Dr. Ahmad. Okay, so we have another last question from Maurice. So from Maurice, what are the efficiency parameters for artificial photosynthesis system to be considered applicable for the industry?
All right, so this is the topic that I intentionally, actually, by intention, it's not covered actually because it's too much. So before artificial photosynthesis, I just want to mention what is the efficiency of natural photosynthesis. Everyone knows that. So the efficiency of natural photosynthesis, like the leaf from the tree now, converting sunlight into the sucrose, to glucose, to energy storage, to rice, let's say, it's only 1%. Even less, 0.9%. So even with 1%, it can produce or supply the oxygen to us. It produces hydrogen. It produces rice, of food for us, with such huge amounts. So this is only 1% efficiency. So from the science behind this is the color of the leaf is green. So only part of the green means that it's the wavelength that can be absorbed is should be less than 560 or 800 nanometers. Correct me if I'm wrong, Dr. Alfian. So it means that only some portion of the sunlight that takes part in the natural photosynthesis because of the color of the chlorophyll, which is green. And the problem now, actually, if you want to increase the efficiency of leaves, the natural photosynthesis, you need to have a leaf that has black color. So the tree should be black because it absorbs all of the portion of the visible light. So with 1%, it's nice. Now we live with that. And for the artificial photosynthesis, the problem is you talk about economical scale, the economy aspects. So something needs to be selling, and something needs to be sold, and something needs to be profitable. And in this case, of course, science then thinking technology think differently now, because you are not going to the basic science anymore, but you are going to the technology, which considers a lot of economical aspects. So for having a commerciable artificial photosynthesis can be applied in industrial scale, mass production. So you need to have at least 10% efficiency, which is at the moment is quite difficult, basically. So the you can achieve 10% efficiency, but once you dip your materials into electrolyte, it lasts only for 1 month. Afterwards, it's decomposed or corroded by the electrolyte, because most of the materials that I mentioned here are unstable. So we need to protect and so on. So there is a long way for that. So the reason why the efficiency is fine so far, I think 10%, the record was, I believe, is 10, 11%. But the long-term stability is the problem. So you have only 1 month's materials for converting the sunlight into the hydrogen with the artificial photosynthesis, but it takes only 1 month, which is uneconomic. So this is 10%. If the short question is 10%, but you need to have the information behind why we achieve this 10%. That's my answer, Dr. Zaki.
Okay, thank you very much for the answer, Dr. Rachmat. Is there any other last question? We have another 5 minutes left. It's a precious time. No?
Maybe
Okay.
this is Friday and 4 o'clock
Right.
there, and then
Yeah.
It's really difficult to find a good time. Actually, if you ask us from Europe to give a presentation at 9 Indonesian time, West Indonesian time, then it would be 4 o'clock or 3 o'clock here,
Right.
which is really
it's too
really,
early.
yeah. So it's too early. So it's always like this. So we can understand this. Yeah.
Okay. Okay. If there is no other question, then we can call it for today's lecture from Dr. Rachmat Adhi Wibowo. I guess before we close this session, perhaps we can do a photo session. It is crucial to have a photo session here. So please, everyone, turn on your camera so that I can take a picture together.
Now everyone shows up. Yeah.
Okay. It
Yeah,
means
they are maybe AFM, Dr. Rachmat Adhi. You know AFM is not Alfian Ferdian Syahmat Suha, yeah? But they are away from microphone.
away
They
from
are online, but they are away from microphone.
Actually, with this new normal behavior, I think it's everywhere is the same. Not only in the University of Indonesia, but it's also the same like here. Like if there is some kind of Q&A sessions, everyone silence. But when we want to shut down the Zoom and everyone say goodbye and everyone, so it's 100 of them. So it's the same. So it's
I guess it's the same. Okay, let's start. Okay, 1, 2, 3, cheers. One more time. 1, 2, 3, cheers. Okay, thank you very much.
all right.
Everyone.
Thank you very much also.
Thank you very much for the nice lecture, Dr. Rachmat Adhi Wibowo. It is nice opportunity to share your expertise here in our department of metallurgy and metallurgical and materials engineering department. So we perhaps we can keep in contact, keep in touch, so that perhaps in the next future, probably in next semester, we will have another session, if possible, with Dr. Rachmat. So we can schedule from now. Okay. Thank you very much, everyone, for joining this lecture. So, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Yeah.
And good morning in Austria.
Yeah,
yes, thank you.
Dr. Adhi, Dr. Rachmat Adhi Wibowo.
Thank you for having me, Professor Herman. So it's nice to be among of the junior again, and then thanks to be virtually back to. It's nice to be back to the alma mater for sure. Yeah. So it's really nice.
Indeed, yeah.
Have a nice day, everyone. Have a nice weekend.
Same to you. Yeah. Same to you.
you.
Yeah. Yeah. Bye-bye.
Bye.
Yeah.
Assalamualaikum.
Waalaikumsalam.
Yan. Si Visu. Ngajak kayaknya tuh.
Di cut. Tapi masih live YouTube tuh, Pak Fian. Aduh. Mikrofonnya rusak nih. Sampai jumpa, Pak Fian. Assalamualaikum warahmatullahi wabarakatuh.